So we're going to start taking notes from right there. So name one of the three pitot static instruments. I just want the name. Jaron. Okay, altimeter's one. Josh, what's another pitot static instrument? There's only three. Altimeter is one. The vertical speed indicator is one, yes. And Mauricio, what's the third one? What kind of an indicator? It indicates the... It's airspeed, okay, all right. Yeah, it indicates airspeed. So today what we're going to talk about is if those holes out on the airplane getting those pressures are blocked. So just for fun, where does the outside air pressure go into the airplane to get to those three instruments? Goes the one that goes to all three. Jordan. What kind of pressure goes to all three instruments? The static pressure, yes. Okay, now, where on the airplane is the static port typically located? Jordan. That was awesome. See, it really does say Jordan. No, it doesn't say Michael. Does anybody want to help Jordan out? What's that? Where is the static port on the airplane usually located? Where on the airplane? It's on the side of the airplane. I'd be really happy. Because do you want ram air going into this? Don't say it out loud. Do you want ram air going into the static port, Jordan? I'm sure it's true. Okay, I'm going to take it out of there for a minute. 3 in a row. I've never had, obviously I'm not stirring it well enough. I haven't baked enough cakes with popsicle sticks. Freddie Rick, what pressure do we not want going into the static port? Ram pressure, right. Okay, so what gizmo on the airplane has ram pressure going into it, Rodrigo? Well, it goes into the airspeed indicator, but where does the air hit the airplane and then get to the airspeed indicator? What's that thing that the air hits? It's a French word that starts with a P. Anybody want to help him out besides Jaron? Jonathan? Pitot tube. Yeah, the pitot tube. I don't know what pitot means in French. All right, so in addition to ram pressure, what's the other pressure that goes into the pitot tube, Jaron? Yeah, there's a second pressure that goes into the pitot tube. Only static goes into the static port. But the pitot tube, ram pressure and another pressure goes into it. Static, yeah. The pitot tube has static pressure in it all the time. And if you start moving forward, it also gets ram pressure. Of course, you could argue if you're not moving, ram pressure is 0. But still static is in there. All right, so that was our review. So we're going to talk about pitot. First, we're going to talk about blockages. Now, I'm going to show you a picture here, and then we'll come back to this slide. So let's take a peek at this picture. So this is slightly different than the pictures we've looked at before, but it just has extra components in it. Whoops. It just has extra components. So let's just try red. So here's the pitot tube, and the air goes in here, and we have ram plus static. Okay. And that goes into the airspeed indicator. So here, this is the airspeed indicator, and here's the static port. And static can go to the vertical speed, or the altimeter, the vertical speed, and the airspeed indicator. And so inside of here is static and ram. There's also a drain hole, a little drain hole. It's usually less than a 1/16 of an inch in diameter. So if water gets in there, the water can leave. Because if the water gets in there and freezes, then we'd be unhappy. So there's usually a drain line. It's a really small hole. So if we're flying along, and the question is, what if this gets iced over? Water gets in there and freezes, and it doesn't get out. How much ram pressure is going to go in there? Anybody disagree with Jaron? How much ram pressure is going to go in there? Yeah, 0 is correct. Okay, so now the airspeed indicator, it's getting static on one side, but is there static pressure in there? There's a drain hole in the back. There's static pressure out here. Is there static pressure in here? Yeah, there's static pressure in here. So we get static pressure in here, but no pitot. So in this case we have ram plus static, remember, minus static equals. So what's ram in this case? No air's getting in? Yeah, ram is 0. So if ram is 0, it's really static minus static is 0. So the airspeed indicator is going to read 0. So if we go back to that slide, if the pitot tube is blocked, but the drain port is open on the back of the pitot tube, then the airspeed indicator is going to read 0. So here's the next one. Well, what if water gets in there and it freezes up, or it's an insect and it clogs up the front of the pitot tube, and it also freezes or clogs up the back of the drain tube? Oops. Let's go back here. So this is clogged, and so is the drain clogged. So we've got static going into the airspeed indicator. At the moment both of these two froze up or got clogged, was there static pressure inside of the pitot system? Yeah, there is static pressure. So there is static in here. But are we getting any ram? No. So we're going to get static on this side, and you're going, hey, well, this looks just like the last time. Well, it does, except for one thing. Here, as we climb up in altitude and as we descend, the static in here won't change, but the static here, it can change, assuming that the static port is still open and static air can get into our 3 pitot-static instruments. So as we change altitudes, one of these pressures is going to change, but the other one is not. So if we go up higher or lower, if both the pitot tube and the drain tube are clogged, if we go up in altitude, the airspeed indicator will go to a higher airspeed reading, and if we descend, it'll go to a lower altitude reading. So let's just say, as an example, we're flying along at 5,000 feet, and both of those freeze up. The airspeed indicator is just going to stay right where it is, because we froze the ram in it, as well as the static. But as we climb and descend, the ram in the pitot tube doesn't change, but the static pressure on the outside of the airplane and going to the other side of the airspeed indicator does. If we climb, the airspeed's going to read a little higher. If we go down to 5,000 feet, it'll read whatever it was reading in the first place. And if we go below 5,000 feet, it'll read lower. Did I lose anybody there? Now, granted, so let's talk about a scenario. We're flying our Cessna 152, like that white and red one out there, the little two-seater. We're flying along in the Central Valley of California at 3,000 feet. What would it take to clog the pitot tube or the pitot tube and the pitot drain? If it happened in flight, it almost has to be ice, because there's not that many insects up there unless you speared a goose with your pitot tube, and then you have other besides the airspeed indicator. Question? There is a heater. It's called pitot heat. Yay, thank you very much. So the only thing you could do in flight is you'd look out there and go, wow, there's ice on my pitot tube. I hate that. And you would reach up and you would turn on the switch, and there's a heating element. Electricity goes through it, and it converts electrical energy into heat, and it heats the pitot tube up. If you think you're going to go flying and you might get icing, that's one of those things you do before takeoff. You turn on the electrical master switch, you make sure the lights are working, you make sure the fuel gauges read how much fuel is in the aircraft, and you would turn on that pitot heat and just touch it. Like, think about it like this. If somebody turned on a coffee pot, a coffee maker, and it had been on for 10 or 15 minutes, and you pulled the coffee pot out, and you looked at where the coffee pot was. You think that thing is hot? It's probably hot. Could you touch it and not get burned? Well, what if you did what? If you touch it really fast, if you just tap your hand on it, could you tell if it was hot? Okay, same thing with the pitot tube. But what you can do with the pitot tube is you turn it on, and about 5 seconds later you walk over to it, you can put your hand around it and hold it. Because at first, it's not hot yet. It hasn't had a chance to get warm. And you can start feeling it getting warm if you hang on for about 30 seconds. Or another way is turn it on, walk around the airplane, make sure all the lights work, you get back to the pitot tube, and then just tap it with your hand really fast, and you can tell if it's getting warm. It doesn't have to get ridiculously hot, it just has to be able to melt ice. There's no exact way to check to see how well it's working. And then you could go turn it off, huh? Well, I can't call up ice and say I want ice on there to turn it on to see if it melts it. I guess I could go out there with you could set up an apparatus to put ice on it, but I don't think it's worth it. Now, what could happen on the ground is, let's say you go out and you pre-flight the airplane, and a mud dauber tries to build a nest in the front of the pitot tube. And let's say builds it in there, and it's far enough inside of it. You look at that tube, and you look in that hole. This one's about 1/8 of an inch in diameter, and you can't see anything. You don't notice it. Now you could take off, and the pitot tube would be clogged, but not the drain. In that case, the airspeed indicator would read, don't say it out loud. Let's see. A mud dauber clogged the front of the pitot tube. You didn't notice it. Frederick, what would the airspeed indicator act like if only the front of the pitot tube was clogged and the drain in the back was not? What would the airspeed indicator do as you were on takeoff, accelerating to 50, 60, 70 miles an hour? What would the airspeed indicator read? 0. Very good, yeah. Because the inside of the pitot system would get equalized, has the drain hole open. I lose anybody there? All right, now I'm going to talk about the static port getting blocked. That's on the side of the airplane. Remember, does ram pressure go into this? Anybody? No, hopefully not. Now you can yaw the airplane really hard and push a little bit in there, but that's most of the time can't happen. So the altimeter. Let's talk about let's go to the picture. So here's the same picture, and I'm going to draw in red again, I think. So we got the static port, but now the static port is blocked. But before it got blocked, there was air in there, but it can't change anymore. So there's static pressure in here, but no, it cannot change. And again, this is one of those things you're going to look at on the side of the airplane. On the airplane, you're going to look in the pitot tube, you're going to look at the drain opening, and you're going to look at the static port during your visual inspection. It's also called a pre-flight inspection. I think we're going to do a pre-flight inspection on Friday on that 152. We'll go around it and say, here's all the things you would check in real life on a typical small two-seat training airplane. In any case, you're going to look at those 3 things, but sometimes you can't see it all. So if it clogs, and if it, let's say, and this actually happened to my airplane less than 6 months ago. I looked at it, and it looked like there was brown mud in it. So I stuck a wire in there and knocked the mud out. And I thought, okay, great, I fixed it. Some bug tried to make a nest, but now I knocked it out, so it's okay. So I went flying, and things did not happen the way I had planned, because farther up in the tube it was still clogged, and I didn't know it. So the pressure inside here stays the same, but as I accelerate and go higher, my airspeed indicator worked. But as I went higher and higher and higher, remember, most of the time on the airspeed indicator, the static pressure gets less as you climb. So I would climb, but the pressure in here stayed high, and it actually made the airspeed indicator get slower and slower as I climbed up in altitude. And then as I descended, I took off out of Reedley and I was going to another airport. And as I came back to the airport going, my airspeed's whack. As I got lower and lower, closer back down to the airport elevation, the airspeed came back up. And that's the problem, is I didn't notice it on takeoff because I wasn't changing altitude, because as you're going down the runway, you're not climbing or descending while you're still on the runway. So my airspeed indicator worked normally until I got off the ground, and then as I changed altitude, the static pressure going into the airspeed indicator didn't change, so it became inaccurate. What's that? Oh, I noticed it right away because I was climbing, the airspeed got less and less, and I'm like, the engine power is correct, my attitude, the nose of the airplane is pointed the right amount. I decided how much to pull the nose up, about 10 degrees. Flying fine. And the stall warning horn didn't come on, and the airspeed indicator was going, it's just really slow. And it's just like, okay, that's whack. And I had never seen that before in 40 years of flying. Well, I was at Reedley Airport. There's nobody there's no tower. So I turned around and came back after I figured it out. But I also remembered it pointed out a thing that happened when I was flying, when I was taking flying lessons, when I was just a punk 16-and-a-half-year-old kid. You guys don't know any of those people, do you? 16-and-a-half-year-old punk kids. In any case, some 17-and-a-half-year-old punk kids, you know them. In any case, so I was 16-and-a-half when I started taking flying lessons. I remember my instructor, we were doing takeoffs and landings and flying around in the traffic pattern at the airport, and he said I was focusing on the instruments too much and I wasn't looking outside. So he took an oil rag that we kept in the airplane, because you always check the oil before you go, and he actually put it over the instruments, the main 6 flight instruments, so I couldn't see them, including the airspeed indicator, including the altimeter, including the attitude indicator. And he made me fly around the traffic pattern like 3 or 4 times and prove that to myself. He made me prove to myself that I could fly the airplane without looking at any of the gauges. Because what happens when you fly low, there's less air going over the elevator and the ailerons and the rudder. So to get the airplane to do what you want, you have to move the controls more. It feels kind of mushy. So that means you're getting slower. So after you fly a while, you start to notice, oh, it's getting mushy. Oh, that means I'm flying slow. There's also a stall warning horn that goes off about 10 miles an hour, 10 knots before you stall. So as long as you don't make the stall warning horn comes on, you're fine. And even if it starts to come on, you just push the nose down a little bit and the stall warning horn goes off. Who needs airspeed indicator? If you can see outside, because it's visual flight rules, the visibility is good, you can see where the horizon is. You don't need the attitude indicator. Now the altimeter's nice. Taking off and landing at the same airport all the time, you can look down and you can say, well, I'm supposed to be at 1,000 feet. Yeah, I'm somewhere between 800, 900, 1,000, 1,100, 1,200, just because you're used to it. Of course, at Reedley Airport, it's easy because you can look out there and see Campbell Mountain, which is next to the airport, and you're right close to the R. So, but even then, you just get used to looking at the ground, and you can tell the difference between 500 feet and 1,000, just because you're used to looking out the window when you're at 1,000 feet. So, if you're just flying day VFR, visual flying rules, if you don't see any of those things, it's not that big of a deal. The problem becomes when you're flying in the clouds, then it's a BFD. If you want to know what BFD stands for, see me after class. So let's go back to this one. So, I was talking about the airspeed indicator. So let's look at the bottom one. So the example I gave was this bottom one down here. As you climb, the airspeed reads too low, and as you descend, the airspeed gets too high. So let's look at what happens to the altitude and the vertical speed. Well, if we have a static port over here that's clogged, and the static pressure inside the system cannot change, then that means the air pressure going to the altimeter doesn't change. Even though you climb, even though you descend, it doesn't change. So if the air pressure, that static pressure going into the altimeter doesn't change, then what's going to happen to the altimeter, Jared? Well, it won't be accurate, but what exactly will it do? The air pressure going into the altimeter doesn't change. So will the altimeter move at all? The static pressure going into the altimeter is stuck at whatever it was when that bug filled up the static port full of mud. So the static pressure inside the static system doesn't change. So the air going into the altimeter doesn't change pressure. Can the altimeter know what the outside air pressure is? So if you climb up or descend, will the altimeter move? No. So that's the answer. The altimeter will stay wherever it was. If it's at Reedley Airport and you take off and it says 380 feet, it's going to stay at 380 feet whether you climb up or go down. It's a lot harder to freeze the static port in flight because it doesn't stick out in the wind. But there are some airplanes that they actually heat the static port up just in case, but they're designed to be able to fly in icing conditions. Little tiny airplanes that you fly around, they're not designed. If you get into icing conditions, you go, ah, and then you turn on the pitot heat, and then you turn around and get out of the icing conditions. And it's not mandatory to say, ah, but it helps a lot. It's on my checklist. Entering icing conditions, say, ah, turn on pitot heat, make a 180-degree turn, and get out of the ice. It's 3 steps there. If you missed the first one, it's not that bad. Okay, so let's talk about the vertical speed. Let's talk about the vertical speed under the same circumstance. A bug has clogged the static port. The air inside of the static system cannot change. The vertical speed, somebody describe for me, what does the vertical speed normally do, Jaron? I can't start. So let's try somebody else. I'm working really hard. I know, I actually put Jordan and Jaron's name in there 4 times apiece. Alex. So what does the vertical speed indicator do? Not necessarily in this circumstance, but you can tell me if you want to. But what's the vertical speed indicator normally telling the pilot? Say that again? Well, it would read 0 in this case. That is correct. Now, under normal circumstances, let's say everything's working correctly, the static port's not stuck. If you were climbing the airplane at 500 feet per minute, where would the needle on the vertical speed indicator point? I know it's hard in this picture because you can't really see the vertical speed indicator very well. Let's put it this way. Does the vertical speed indicator tell the pilot if the airplane is climbing to a higher altitude? Does it tell the pilot if it's descending to a lower altitude? Okay. So does the altimeter. But the altimeter doesn't tell you how fast you're climbing, and it doesn't tell you how fast you're descending. So you said it would read 0. Can you explain, if the static port was clogged, can you tell me why this would stay at 0? Well, the static port is clogged, but what does that do? If the static port is clogged, what does that do to the air inside of the static system? Can it change? No, it can't. That's correct. Okay. So the air pressure going into the vertical speed indicator, does it change? No, it doesn't. So this needle right here is really telling you how fast the static pressure is changing. But this thing's clogged up, so it doesn't get any change in air pressure, so the needle never moves off of 0. So if I go back a slide, I think I can go back a slide. Uh-oh, it's doing something. The computer's freaking out. I must have pushed the wrong button. If I go back a slide, you've got it in front of you. Both the altimeter and the altimeter will freeze, or correction, you could say the altimeter will stop moving. It'll read whatever altitude it was when the static port got closed. And the vertical speed indicator, since there's no change in air pressure going to it, it'll stay at 0. Wonder what's going on with my computer. Well, I'm just going to keep talking. So we just did the static blockages. All right. So the next item, although this doesn't want to do it, is the magnetic compass. It doesn't want to cycle. Try one more time. Yeah, we're going to tell it to stop. Yeah. Yeah, but I'm going to try to give away test answers while you're gone. It's going to be my goal in life. Now that I put the slide up, I realize I didn't include a picture. How many people in here have never seen a compass? You have never seen a compass in real life. It's okay if you've never. How many people have never gone hiking and used a compass? Wow. Okay. What? Say that again? Yeah, you could. You have a compass on an iPhone, I think. It's measuring magnetic lines of flux off of the Earth's iron core. Everybody likes the Earth's iron core. All right. So magnetic compasses, the mechanical ones, not the electronic ones, they have a magnet that floats. Since it floats, it means it can spin around to wherever it wants to point. What people usually don't think about is where compasses actually point. So for instance, yes? Question? Well, the magnetic North Pole is close to the true North Pole of the Earth, but it's not exactly in the true North Pole. So if we look at the side of the planet, and here's the equator, the true North Pole is right here, and the magnetic North Pole is right about there, the magnetic North Pole. And if we're in, I'm just going to draw the contiguous 48 states right there, and we're over here in California. True North is right there, and magnetic north is actually off about 13 degrees. If I drew a different picture, and I'm sure you're drawing these pictures, that if we had the magnetic North Pole, these lines of flux are actually coming out and going in, and they're coming out and going in. So you'll know, that's a pretty lousy picture. In any case, if I had, let's try a different picture. If I have the magnetic North Pole up here, and I have a compass, remember this is the North Pole, this compass, the south is going to be attracted to the north. So on magnets and compass, it's actually the north seeking end of the magnet is actually the South Pole. So if you took a big magnet and hung it from a string, and you let it hang and got rid of all the friction, the South Pole would actually be pointing towards the North Pole. And that works out okay. Because if you're the pilot, you're right here with a couple of eyeballs, and you're looking in this direction. So you see something that's labeled north. So you put this on a card all the way around, and north, south, and this would be west, and this would be east. Maybe I'm just confusing you there. So that brings up my point here. What that really means is when you're looking at a compass in an airplane, you're looking at the back side of where the magnet is, but it's telling you which direction you're going. How many people have navigated using a compass? Do you mind explaining where you navigated with a compass, Alex? Yeah, well, can you explain it? Were you hiking last week on Mount Everest? Okay, was it last year in Yosemite National Park? 2 weeks ago in Bear Creek, and you had a compass, and you're using it to figure out which way to go? Okay, did you get lost and have a fatal accident? Okay, was there somebody else? You used the compass? Was it hiking? You pulled out your phone, your compass phone. Yeah, don't you love those computers? They're awesome. Yeah. Okay, good. So you used it to try to look at a map and figure out which way to turn the map. And yeah, you're right. The sun rises and it looks like it rises in the east, and it looks like it descends in the west, but it's not exactly in the east, and it's not exactly in the west. And technically, the sun doesn't move; the Earth rotates. That's okay. Your whole life, you look outside. You're 4 years old, and somebody says the sun is rising from the east, and that's where you start your misinformation, because the sun's not actually rising. It just looks like it. The sun's actually rotating. Question? Center of gravity, yeah. So effectively what that means when it says that the magnet floats, there's like a pin, and we have a magnet, a card like this, and there'll be north on this side and south on that side. And so this can rock back and forth, and right here is the center of gravity, right here. And so it can flop around a lot, and that's one of the things that causes the errors, is that it can oscillate and it can dip, and we'll get to that before compasses are over. All right, I'm going to show you what in the world this means. So we're going to come back to this slide. I want to look at a picture first. All right, so let's talk about magnetic variation. So magnetic variation was that diagram I showed you before. If this is the Earth, and here I'll put the contiguous 48 states. Oh, I forgot Texas. So we're over here in California, and here is the true North Pole, but the magnetic North Pole is actually in northern Canada. So if I drew a straight line to the true North Pole, and then I drew a straight line to the magnetic North Pole, they'd be off a little tiny bit. And you're going, well, true versus magnetic, what's the difference? True north is the North Pole where the Earth rotates about. Have you ever seen an insect collection where people stab a needle through a bug, through an insect? Well, if you spun that needle around, the bug would spin around, right? It would spin around its axis. So where that needle entered the thorax of that insect, that's the true North Pole of the insect. It's also the true North Pole of the Earth. If you look at a globe that's on a stand and it spins, the spot where the metal comes in and it spins around, that's the true North Pole. When we talked about in aviation history about somebody flying over the North Pole, I think it was the Roma, in the 1920s or something like that, they were looking for the true North Pole. See, the magnetic North Pole is where the iron magnet of the Earth is not aligned, it's not in the same place. It's actually on an island or two in northern Canada. So your compasses, your magnetic compasses, if you flew or drove a car or sailed a ship, and you kept north pointed on it the whole time, you'd end up in northern Canada and you'd stop because you'd go past the magnetic North Pole, and now while you're trying to get to the true North Pole, the compass would say, hey, turn around, you passed the magnetic North Pole. The good news for us is it's pretty close. Here in Central California, it's about 13 degrees difference. The way I remember it is Santa Claus lives at the true North Pole, and that's why it's really hard to find Santa Claus, because all of the magnetic compasses point you to the magnetic North Pole, and that's in Canada, and lots of people have been there. But hardly anybody gets to go to the true North Pole to where Santa's hanging out with it. Does anybody know anybody that's ever been to the true North Pole? See? See, that must be true. So it is true that Santa Claus lives at the true North Pole. And he would never live at the magnetic North Pole, because then everybody would be able to find him. So several people are going to have to double up here, because I think I only have 9 charts. So 3 of you're going to have to scooch up next to somebody else with a chart. I want you to find Fresno Air Terminal. I want you to find Fresno Yosemite Airport. Go ahead and get up and move to another chat desk. This is an aviation chart. This is an aeronautical chart. I want you to find Fresno Airport. I want you to find Fresno Airport. There's some magenta colored rings around it. It actually has 2 magenta colored rings around it. And there's a big yellow blob where the city of Fresno is. Yep. There's a big yellow blob where the city of Fresno is. Yeah, that's it. Yep, that's it. Would you make sure Luke knows where it is? The yellow means it's a big city. I hate to use the word congested because there are other places that are congested, but that's definitely congested. Absolutely, if you were flying over it, you would have to stay at least 1,000 feet above the highest obstacle that you were within 2,000 feet of horizontally. Did you guys find Fresno? Yeah. All right. You guys find Fresno? All right. So what I want you to do is sit down someplace where you can look at a chart. You may have to sit down next to something because all I have is 9 charts, and there are 11 people in class at the moment. So I'd like you to sit down, and it's okay to fold the chart up a little bit, but I want you to be able to look at the chart and listen to what I'm saying and look at what I'm showing you on the screen, because I have up on the screen the Fresno Yosemite International Airport. So I'm going to show you one thing, and then I'm going to show you about 10 more. So could you guys have a seat, sit next to somebody that has a chart if you don't have one yourself, and get it open so you can see the Fresno Airport. Thank you. So please don't draw on this, and you don't have to take notes at the moment, but you'll notice, I'm going to see if I can do this. Let's try white. You'll notice, no, white's not working. Now we'll try black. You notice there's a dotted line over here next to Dinuba, and it's magenta. That's kind of a purplish red. And you'll notice it says 13 degrees east. Jonathan, question? Yeah. Yeah, go ahead and hit it. So you notice it says 13 degrees east. So I would like everybody to put their finger on that 13 degrees east. That 13 degrees east is telling us the magnetic variation. That's what I was talking about 5 minutes ago. That tells you if you're standing on that line, anywhere on that line, and you pointed due north or true north, you would have to aim to the east 13 degrees, and that's where your compass would point to the North Pole. Now, you got to be clear, this is a little confusing. This line is not telling you, follow the line and you'll get to the North Pole. That's not what it's telling you. It's telling you if you're standing on the line and you point true north and point to the east, that's to the right, point to the east just a little bit, 13 degrees. Because look at this. You'll notice, if you don't mind looking at the screen here, you'll notice, let's look at this line right here. You see this line going up? Is anybody not able to see that line? There's a line right there, and there's a bunch of little tick marks on it. Okay, that line is pointed to the true North Pole. That line is pointed to the true North Pole. This is a line of longitude. It goes all the way from the true North Pole to the true South Pole, and it's 12,000 nautical miles long. It's 12,000.00 nautical miles long, because the half of the Earth's circumference is 12,000 nautical miles. That's how nautical miles came about, is that you divide the Earth up at the equator. In any case, so that's true north. So I'm going to write true up here. You're not going to write on yours. Now, if I'm standing on this line right here, it does not mean that the magnetic North Pole is that away, because this is way more than 13 degrees. What it means is if I measured the difference here, 13 degrees, that would now be pointing to the magnetic North Pole. And if you look up, if I take this line right here and I go 90 degrees to it, and I follow it, whoops, I bet you I'm going to follow. You ought to be able to find another one. It's either going to say 14 or it's going to say 13 and a half. Can you find one that says 13 and a half or 14? That's farther north and west, that is up and to the left. What does it say, Jaron? 14. So I want you to look and find that line of variation, and it says 14. So who can't find it? Yeah, there's another magenta line up and to the left that looks like this 13 one. It says 14. Can't find it. Yeah, 14 east. Thank you. 14 east. What that means, the variation or the difference between pointing at the true north pole and pointing at the magnetic north pole, it's worse. It's 14 degrees. So if you were somewhere halfway between these two lines, how many degrees of variation do you think it would be if you were exactly, I know this is tough, if you're exactly halfway between 13 and 14, how many degrees of variation would it be? Halfway between 13 and 14, 13 and a half. Now we're doing this because when we figure out we're going to go on a flight, the wind that we get is based on true north, but the compass in the airplane and the other navigation instruments we have in the airplane are based on magnetic north. And 13 degrees is quite a difference. These lines, it's on your notes, we'll get back to it. These lines are called isogonic lines. These lines are called isogonic. Iso means one. It means if you're on that line, there's just one variation between true and magnetic north. So if you're on that 13 line, anywhere on the line, there's one magnetic variation. So every time you go to plan flights, you're going to have to take into account that the winds are going to be in true, how far are they off from the true north pole, versus how far they are off of the compass and all the other systems in your airplane. So how many people have ever looked at, this is a navigation chart for small airplanes. How many people in here have ever looked at one of these? Just one. How many minutes have you spent looking at an aviation chart, Jonathan, in your whole life added together? 27? 270? Not more than an hour. Okay. So what I'd like to do is look at a couple of other things. I'm going to get rid of this marking. And what we're going to do is we're going to look at the Fresno Yosemite International Airport. So I'm going to draw a big arrow to it. And Fresno Yosemite International Airport, it has two runways. You can see it's in blue. The blue means it has an air traffic control tower. That means there's somebody you have to talk to either fly in or to take off. You'll notice that Reedley Airport, I'll tell you what, we'll go Selma Airport down here. Here's Selma International. You'll notice it's magenta. Magenta is kind of just a reddish purple, but I'm going to start saying magenta because that's what the FAA calls it. Selma International Airport, it's not really an international. You notice it's magenta. That means there is no air traffic control tower. That means you don't have to talk to anybody, and you don't have to do what they say because there's nobody to listen to. So that's the difference, and you'll notice that that in both of these symbols, the inside of it without the color is telling you the approximate length and direction of the runway. All right, so let's go back to Fresno Yosemite. You'll notice that in blue, which is the same color as the airport, in blue font, it says Fresno Yosemite International, and then it says FAT. FAT. The name of the airport used to be Fresno Air Terminal. In the United States, all airports have a 3-digit identifier. And some of them line up with what the name of the airport is, and some of them don't. So for fun, we looked at Fresno Air Terminal, now it's Fresno Yosemite. FAT makes sense. But let's look at Selma International. Selma, there's the name of the airport, Selma Airport, but it's 0Q4. Did I read that correctly? That's a 0 with a line through it, so that's 0Quebec 4. In aviation, it's hard to understand people on the radios, so if I was going to read the name of this airport to somebody, so I was talking to somebody, I would say I want to land at 0Quebec Airport. I'd probably say the word Selma Airport. I'd probably say I want to land at Selma Airport, 0Quebec 4. Now, granted, if I'm talking to somebody out of Fresno, the air traffic controllers know where Selma Airport is. So I probably wouldn't say 0 Quebec 4. But if I'm going to call somebody up, if I'm in Arizona and I'm going to fly to California and I want to tell them what airport I'm going to, I wouldn't say Selma Airport because they might think it's Selma in Alabama where civil rights things happened back in the 60s. This is a completely different Selma. So I would say I'm going to fly to Selma Airport 0 Quebec 4. And Quebec, has anybody ever noticed on cop shows, you know, A, B, C, D, E, F, G, they don't say A, B, they say Alpha, Bravo. Yeah, well, aviation has a different set of code words. I don't know what the cops use. No, well, the military uses the same one as aviation. Let me rephrase that. The only military I know was aviation military, and so we use the same code as the FAA does. Alpha, Bravo, Charlie, Delta, Echo, Foxtrot. Z is Zulu. All right, yeah, Z, the letter Z is Zulu. And you don't say Quebec, you say K-Bec, as if it was spelled K-A-Y. There's correct pronunciations. It's like the letter 9 and the correct number 9 and the number 5 both have the I sound in it. So on the radio, you say Niner, and on the radio, you say Fife. F-I-F-E. I'm not making this up. And the same thing with 3. You don't say 3, you say tree. Now in the United States, if you don't say Niner or 5 tree, the air traffic controllers usually can understand you. Although the difference between 5 and Niner is sometimes tough over the radio. Has anybody in here used the CB radio before? So Alex, are you raising your hand? You've used the CB? Oh, okay. So is it sometimes hard to understand people? Okay. Think about listening to a radio station in Bakersfield and it's transmitting out of Fresno. The closer you get to Bakersfield, the harder it is to understand them. There's a lot of static. So that's the reason all of this got started. Because radios are a lot better now than they used to be, or you could say because radios were worse. All right, so let's look at another detail here. Let's look at another detail. So you'll notice Jonathan asked me, look at all this big yellow area around Fresno. That is not the city limits. These yellow areas are places where there's a lot of people and buildings. That's a congested area. That's a congested area. Now, there are other areas that are congested, but there's a federal aviation regulation that says if you're flying over a congested area, you have to be at least 1,000 feet above the highest obstacle. So what's the highest obstacle? What do you think? In downtown, what is that building? What's that big building there? I know what it used to be called. They named it after the guy the developer, Del Webb. It was called the Del Webb Townhouse. It was 10 stories tall with towers on top of it. So it was like 100 and some odd feet tall. Well, you can tell by looking at it, and sure enough, look at this right here. You see these two what look like mountains with dots? It's 353, and next to it is 642. The 642 is the mean sea level altitude of the top of those towers, whatever it is. Maybe that's the Del Webb Townhouse with towers on top. So what that means is I need to add 1,000 feet to that if I'm going to fly over it. And then you're thinking, well, how close do I have to get to it before I have to fly above it? You have to be within 2,000 feet to the side of it. So 2,000 feet, a statute mile, is 5,280. So 2,000 feet is not quite a half of a mile. So if I'm going to get within a half of a mile or so of that obstacle, I have to climb to 1,642 feet. Because it's in a congested area. Now you got to be careful. There are places on this map that are yellow that might be congested areas. So the FAA's definition of a congested area is if there's a whole bunch of people there. So, Valley, where I live, they have a rodeo, and there's 400, 500, 600 people all together. The FAA would call that a congested area, and now you would have to be 1,000 feet above the highest obstacle if you're within 2,000 feet of that obstacle. So just because it's not yellow doesn't mean it's not congested. But generally speaking, if you're out in the middle of nowhere, and there's a farmhouse here and a farmhouse there, when you're not over congested areas, you only have to stay 500 feet away from any vessel, vehicle, structure, or person. And I want you to understand this difference here. The rules, these two rules are written different. It says if you're over a congested area, you got 1,000 feet above. It uses the word above the obstacle that you're within 2,000 feet horizontally. Way. Which means I could fly out over in the middle of a lake, and if there's no vessel, vehicle, structure, or person, I can legally fly as low as I want to. Now, at some point, the FAA is going to say that's careless and reckless, and that's a whole other regulation. But I could fly down to 300 feet, and then somebody could call the FAA and give them the N number off of my plane, and I could say I was more than 500 feet away from any vessel, vehicle, structure, or person, and if the engine quit, I was prepared to ditch in the water. And therefore, it was not careless or reckless. Now, am I saying that that's a good idea? Am I saying that's safe? No, I'm not saying that. All right. Yeah, go ahead, Jonathan. There's a couple of what? 2 dots next to the airport? I'm not sure what dots you mean. Those 2 dots right there? That's a really good question. I don't know. So guess what? If you look at a chart and you don't know what it is, there's a legend. There's a legend that hopefully will have that on it. The problem is the legend doesn't have everything on it. Outdoor theater, you found it? That sounds like I wonder if that's the fairgrounds. No, that's not the... Oh, that's drive-in. Those are drive-ins. Those are the 2 old Sunnyside drive-ins that are now flea markets. But they're still there. They're still there. Do they show? Okay. So those are outdoor drive-ins. All right. So let's go back. I just want to cover a few more things, and then we're going to call it. I want to look back at these blue words and stuff talking about the airport. So we know what the airport is. We know that Alpha Tango, FAT. And you see it says CT. CT stands for Control Tower, and it's 118.2. And these frequencies are right above the FM frequencies. On your car radio, how high do the FM frequencies go? 107.9, or you could call it 108. So this is only 118, so it's only a little bit above FM frequencies. So that's what it's 118.2 megahertz. You also notice it says ATIS, Automatic Terminal Information Service, ATIS. And what that is, it's about every 30 minutes or an hour, or if the weather changes, one of the ground controllers in the tower will make a recording, and then on this frequency, it'll just play over and over again. It lasts about 20 or 30 seconds. It'll say Fresno Air Terminal, Yosemite International. It'll say what time it is, Zulu time. And it'll say this is what the wind is, this is what the altimeter setting is. So if I'm coming into land there, I can crank in my altimeter setting on the Colesman window, and it'll tell me at Fresno, it'll tell me what runways are they using. Did I say wind, altimeter setting, what runways they're using? And it'll say the name of the information. It'll say information echo. And then it'll tell you all this stuff. It'll say information echo. And then it'll start up over again. So when you're coming into land, their traffic controllers, or you're going to take off, they want to know that you have the correct altimeter setting, so you're going to fly the right altitudes. And they don't want you to be asking them what runway is in use. And they don't want you to ask them what the wind is doing. So when you first call them up, it would sound like this. You would say, Fresno Approach Control, Cessna 3435 Juliet, that's my license plate number. Echo. That I have, you could say, I have information echo, or you say, with information echo, or you just say the words information echo. Pow. They know that you've got the altimeter setting, you know what runways they're using, you know what the wind is doing, and they don't have to tell you any of those things. And they don't want to tell you any of those things because they're busy talking to other airplanes. So what you're going to do as a pilot, about 15 minutes before you get there, especially if you've got two radios, one of those radios you're going to crank in to the ATIS, which is on 121.35, and you're going to turn the volume up and you're going to listen to it, and you're going to write down you're going to write down an E on your clipboard. So when you call them up later, you'll tell them that you have information echo. You'll notice right next to it, there's another frequency, 273.6. Does anybody know what that is? I'll give you $1. I got $1 right now. Somebody tell me. Well, I only offered $1 because I figured nobody would know. You have 10 more seconds. All right, Jonathan? Like in-flight services, like meal service, you get coffee and tea? Huh? Fuel. No, that's the Unicom frequency. 7, 6, 5, 4. No, it's not emergency. The emergency frequency is 121.5. 3, 2, what? Last chance? Nope. This is the military frequency. The U.S. military aviation frequencies use much higher frequency radio transmission frequencies than civilian airplanes do. So for instance, the emergency frequency, if you're flying along and the engine quits and you don't know who to talk to, you crank in 121.5. That's 121.5 megahertz. But the military equivalent to that is in the 300 and some odd range. So the frequencies we use in little airplanes, or airliners for that matter, is VHF, very high frequency. What they use is ultra high frequency, UHF. What I'd like you to do is try to fold the chart up back to the way it originally was so you can see the legend on one side and the title page on the other. And then we're going to be in the computer lab at 31 after in real life. We're going to get these where you can buy them online, or there's probably a store or two in Fresno. Most flight schools will sell this to you. I haven't looked lately. They're probably 15 or 20 bucks. You're almost there. You're really close. Are there geese depicted on this chart? Yes, and they're Philly. When was the last time you folded an aviation chart, Luis? Today? Okay. Well, don't feel bad. I folded these a million times. So you're almost there. Ta-da! Thank you, gentlemen. 31 after on a real clock in the computer lab.